Consistent and inconsistent systems. Welcome, everyone. Today, we are moving into a very important topic, consistent and inconsistent systems. Now, in our previous lessons, we focused on a specific method for solving systems of linear equations, specifically using the matrix equation, A times x equals b. Up until now, we have mostly been looking for that one perfect answer. However, it is crucial to realize that not every system of equations results in a single, unique solution. In some mathematical scenarios, you might find that a system has an infinite number of solutions, meaning there are endless possibilities that work. In other cases, you might encounter a system that has no solution at all. It simply cannot be solved. The entire branch of mathematics that investigates whether a solution exists in the first place is known as the study of consistency. Over the next few slides, we will learn exactly how to distinguish between these different types of systems. Understanding the concept of consistency. Now that we've established that we aren't always looking for a single, unique answer, let's dive into how we actually categorize these systems. In mathematics, we classify a system of linear equations based on one simple question. Does a solution actually exist? First, we have what we call a consistent system. We use the term consistent if there is at least one set of values for our variables that satisfies every single equation in the system at the same time. Now, don't let the word at least one trip you up. This category actually covers two different scenarios. The first is when the system has a unique solution, meaning there is exactly one specific value for each variable. The second is when the system has infinitely many solutions, meaning there are endless possible values that work. As long as there's a solution to be found, the system is consistent. On the other hand, we have an inconsistent system. This is the case where there is no set of values that can satisfy all the equations simultaneously. In simpler terms, there is no solution at all. In the next few slides, I'm going to show you the specific algebraic tools we use to distinguish between these different types of systems using matrices. Linking consistency to matrix algebra. Now that we understand the basic definitions of consistent and inconsistent systems, you might be wondering, how do we actually test for this using the matrix methods we've been practicing? On this slide, we bridge the gap between the concept and the calculation. To determine if a system, represented by the matrix equation A times x equals b, is consistent or inconsistent, we don't need to guess. Instead, we primarily look at two specific mathematical indicators. First, we examine the determinant of the coefficient matrix A, which we denote as the vertical bars surrounding A. Second, we look at the product of the adjoint of matrix A and the constant matrix B, which we write as the adjoint of A, all multiplied by b. These two values, the determinant and this specific product, are the keys that will tell us exactly which category our system falls into. Case I, the nonsingular case, a \next 0. Now that we understand the general concept of consistency, let's dive into our first specific scenario. On slide 4, we are looking at what we call the nonsingular case. This occurs when the determinant of our coefficient matrix A is not equal to 0. When this happens, the matrix A is what we call invertible, meaning it actually has an inverse. Because this inverse exists, we can use a very straightforward formula to find our variables. X equals A inverse multiplied by b. Since this formula allows us to calculate exactly one specific value for our variables, we can conclude that a unique solution exists. Therefore, in any situation where the determinant is non-zero, the system is always classified as consistent. Case II, the singular case, A equals 0. Now, let's move on to case II, which is the singular case. This happens when the determinant of our coefficient matrix, A, is equal to 0. As we touched on in the previous slide, when the determinant is 0, the matrix A is singular, meaning it does not have an inverse. Because we can't use the standard formula, x equals A inverse times b, we can't immediately tell if the system has no solution or infinitely many solutions. To find out, we have to take an extra step and calculate the product of the adjoint of A and the constant matrix B. So, our first step here is to calculate the product of adjoint A and B. To do this, you'll need to first compute the adjoint of matrix A, and then multiply that resulting matrix by our constant matrix. This calculation is crucial, because as you will see in the next slide, the result of this product will tell us exactly whether our system is inconsistent or consistent with infinite solutions. Analyzing the result for singular case. First, let's look at the case where the product of the adjoint of A and the matrix B is not equal to 0. If you find that this result is non-zero, it means the system is inconsistent. In practical terms, this implies that there is no possible set of values for our variables that can satisfy all the equations at the same time. The equations are essentially in conflict with one another. On the other hand, let's consider the second case. What if the product of the adjoint of A and the matrix B is equal to 0? If this happens, the system is considered consistent. However, I want you to pay close attention here. Being consistent doesn't necessarily mean we have a single, unique answer. In this specific scenario, because we already know from our previous slide that the determinant of A is 0, the system doesn't have just one solution, but instead, it possesses infinitely many solutions. Now that we have calculated the product of the adjoint of A and the matrix B, we need to interpret what that result actually tells us about our system. This is the crucial part of the analysis. In the next slide, I will provide a summary table that brings all these conditions together so you can see the full picture at a glance. Summary table for quick reference. Now that we have walked through the different cases, let's bring everything together with this summary table. This is your go-to reference for any exam or problem-solving session. First, look at the top row. When the determinant of matrix A is not equal to 0, we call this the nonsingular case. In this scenario, we don't even need to check the adjoint part because the system is guaranteed to be consistent and you will find exactly one unique solution. Next, let's look at the second row, which is a critical case to watch out for. When the determinant of matrix A equals 0, the matrix is singular. If upon checking, you find that the product of the adjoint of A and matrix B is not equal to 0, then the system is inconsistent, meaning there is no solution at all. Finally, the third row shows the third possibility. We are still in the singular case where the determinant of matrix A equals 0, but this time, the product of the adjoint of A and matrix B equals 0. In this specific instance, the system is actually consistent, but instead of one solution, it possesses infinitely many solutions. Keep this table in mind, as it perfectly summarizes the logic we will apply in the following example. Real-world analogy, the intersection of paths. Now, I know all these algebraic terms like singular matrices and adjoints can feel a bit abstract, so let's take a moment to step away from the numbers and visualize what is actually happening. To make this concept more intuitive, imagine two people walking on a flat, two-dimensional plane, where their paths represent the lines in our linear equations. First, let's look at a unique solution, which we've identified as a consistent system. Imagine these two people are walking on straight paths that happen to cross at exactly one specific point. Because their paths intersect, there is one single, clear meeting point. That point is our one and only solution. Next, consider the case of no solution, which we call an inconsistent system. In this scenario, imagine the two people are walking on paths that are perfectly parallel to each other. Because they are running in the exact same direction but separated by a constant distance, no matter how far they walk, they will never, ever meet. This lack of an intersection is why we say there is no solution. Finally, let's look at the case of infinite solutions, which is also a type of consistent system. Imagine that these two people are actually walking along the exact same path, one right after the other. Since they are on the same line, every single point along that path is a point where they occupy the same location. Because they are always meeting, at every step, we have an infinite number of solutions. With this visual mental model in mind, Let's move on to a concrete numerical example to see how we apply these rules using matrix algebra. Step-by-step example of analysis. Take a look at this system of linear equations. X plus y equals 2 and 2x plus 2y equals 4. Our first step is to translate these equations into the matrix form, Ax equals b, which we've been using in our previous lessons. To do this, we extract the coefficients into matrix A, the variables into matrix X, and the constants into matrix B. So, our matrix is a 2 by 2 matrix with 1 in the first row and 2 in the second row. Our variable matrix X contains X and Y, and our constant matrix B contains 2 and 4. Next, we move to step 2, where we need to find the determinant of matrix A, denoted as the vertical bars around A. We calculate this by multiplying the elements of the main diagonal and subtracting the product of the other diagonal. That gives us 1 times 2 minus 1 times 2, which simplifies to 2 minus 2, resulting in 0. Now, remember what we discussed in the previous slides regarding the singular case. Because the determinant is exactly 0, we know that matrix A is singular and does not have an inverse. This means we cannot simply use the formula X equals A inverse B to find a unique solution. Instead, as we'll see in the next few slides, we are now required to calculate the product of the adjoint of A and the constant matrix B to determine if this system is inconsistent or if it has infinitely many solutions. Now that we have covered the theory and the different cases, let's put everything we've learned into practice with a step-by-step example. Finding edge A. If you are working with a 2 by 2 matrix, where the elements are a B, C, and D, there is a very simple shortcut to find the adjoint. You simply swap the positions of the elements on the main diagonal, that's A and D, and then change the signs of the other two elements, B and C. So, our new matrix becomes D, negative B on the top row, and negative C on the bottom row. Let's apply this rule to the specific matrix A from our previous step. Looking back at our matrix A, which was 1, 1 on the top row and 2, 2 on the bottom row, we apply the swap and sign change. We swap the 1 and the 2 on the diagonal and change the signs of the other 1 and 2. This gives us our adjoint of A, which is 2, negative 1 on the top row and negative 2, 1 on the bottom row. We will need this result for our very next step, where we multiply it by matrix B. Now that we know we need to calculate the product of the adjoint of A and matrix B to proceed, let's focus on how to actually find that adjoint. Calculating edge AB dollar. Now that we have identified the adjoint of matrix A in the previous slide, let's move on to the final calculation to determine the nature of our system. We need to multiply the adjoint of A by our constant matrix B. Looking at the calculation, we take our 2 by 2 adjoint matrix, which contains the elements 2, negative 1 in the first row and negative 2, 1 in the second row, and multiply it by our column matrix B, which contains the elements 2 and 4. To find the values for our new resulting matrix, we perform dot products for each row. For the first row, we multiply 2 by 2 and add it to negative 1 multiplied by 4. For the second row, we multiply negative 2 by 2 and add it to 1 multiplied by 4. As we simplify these, the first row becomes 4 minus 4, and the second row becomes negative 4 plus 4. This leaves us with a resulting column matrix where both entries are 0. This specific result is crucial, as it leads us directly to our conclusion in the next slide. Conclusion of example analysis. Now, let's bring everything together to reach our final conclusion. Looking back at our calculations from the previous slides, we found that the determinant of matrix A is equal to 0, and when we multiplied the adjoint of A by matrix B, the resulting matrix was a 0 matrix. Because we have met the specific condition where both the determinant is 0 and the product of the adjoint and the constant matrix is 0, we can officially conclude that this system is consistent, and specifically, it possesses infinitely many solutions. This means that instead of the paths crossing at just one point, these two equations actually represent the exact same line. Key takeaways. First, remember the core definition. Consistency simply refers to whether or not a solution exists for our system. If there is at least one solution, we call it consistent. If there is none, it is inconsistent. First, when the determinant of matrix A is not equal to 0, it means the matrix is non-singular and invertible. This leads directly to a unique solution, and therefore, the system is always consistent. Second, if the determinant of matrix A is equal to 0, we have a singular case. In this scenario, if the product of the adjoint of A and the constant matrix B is not equal to 0, then the system has no solution, making it an inconsistent system. Finally, if the determinant of matrix A is equal to 0, but the product of the adjoint of A and the constant matrix B is exactly equal to 0, then the system is consistent, but it possesses infinitely many solutions. All right, class, we have reached the end of our lesson, so let's bring everything together with a quick summary of the key takeaways. Now, let's look at our 3 mathematical conditions for quick identification. Keep these 3 pathways in mind, as they are the foundation for analyzing any linear system you will encounter. Before we finish, I want to point out a few common pitfalls to avoid during your exams. Common mistakes. First, the most frequent mistake I encounter is assuming that if the determinant of matrix A equals 0, there is no solution. This is a misconception. As we discussed in the singular case earlier, a 0 determinant simply tells you that a unique solution does not exist. It doesn't tell you the whole story. To truly know if you are looking at an inconsistent system with no solution, or a consistent system with infinitely many solutions, you must perform that extra step of checking the product of the adjoint of A and the constant matrix B. Second, try not to confuse the terms consistent and unique. It is easy to get these mixed up, but remember, consistent is a broad category. As we saw in our definitions, a system is consistent as long as there is at least one solution. So, even if a system has infinitely many solutions, it is still technically a consistent system. Finally, please be extremely careful with your arithmetic when calculating the adjoint. When you are finding the product of the adjoint of A and matrix B, even a tiny error in the signs of your cofactors will lead you to the wrong conclusion. A single misplaced negative sign can make an infinite solution look like no solution, or vice versa. Always double-check your signs before you finalize your answer. Now, before we wrap up today's lesson, I want to pause and highlight a few common pitfalls. I've seen many students stumble on these specific points during exams, so please pay close attention. If you can avoid these 3 traps, you'll be well on your way to mastering the analysis of linear systems.